you know that during chemical reactions, bonds are broken down. So that breaking of bond in a chemical reaction is known as bond fission. Is inversely proportional to what? Energy. Okay. So that is highly energetic. The next thing which you should understand, that it is not like this always that intermediate is necessarily formed. It is not the necessity. It can happen during any chemical reaction that reactant gives you the direct product. Here there is no intermediate, then it's okay. Or it can happen that it gives you only one intermediate, that's also possible. Or it can happen that it gives you first intermediate, then it gives you second intermediate, then it gives you the product. So it can happen. Now we need to discuss that what is this carbene. That is a new term for you, I think, right? So let's discuss about carbene. So this carbene is represented by H2S plus minus. What is the structure of this carbene? In fact, it is here hydrogen, here it is positive, and here it is negative. If I want to draw the diagram, so the diagram will be this one. Here it is empty. Okay. Here 2 electrons are there. Fine. Here S is 0, that is spin, and it is singlet. Because when we calculate, the spin is 0. So what we get? We get it as 1. Therefore we say that it is a singlet carbene. There is another type of carbene also, that is a free radical. It is known as triplet carbene. Why? Because here in the orbitals one electron is there. So what is the spin? The spin can be in any direction and it is 1. Fine. So if you calculate magnetic moment, it will be 2s plus 1, that will be 3. So here 3 comes. Therefore it is known as triplet. Okay. Now let's discuss about CH3 positive, CH3 negative and free radical. Right. So first of all, you tell me that what is the electronic configuration of carbon in ground state. So it is what? It is 1s2, 2s2, 2p2. So what is the diagram if I make? That is 1s, this is 2s and this is 2p. Right? This is ground state. Now suppose this carbon goes into excited state. So what will happen? This electron will unpair and it will come here. So what you will get? You will get the diagram just like this. Right? That will be your diagram. So here, how many bonds carbon can form? Carbon can form 4 bonds. Okay. Now, what happens in CH3 positive? That is, here 2 are there. This is what? This is 1s. In 2s, what is the condition? 1 is there because it is excited and it is reacting with hydrogen, right? In 2p, this is the diagram, and these 3 hydrogens gave their electrons here. Suppose this is the hydrogen's electron. 3 gave their electrons, right? And 1 electron is remaining. So, this 1 electron which is remaining is unpaired electron, right? We know that unpaired electron is paramagnetic in nature. So it is paramagnetic. Now let's discuss the case of CH3 free radical. Free radical means carbon, hydrogen, bonds, 3 bonds are there and 1 electron is with carbon. Means this carbon electrons and this carbon electron are there bonded with the hydrogen one, right? This is the scene here. But here nothing is there, okay, no bond is there, fine. So there is 1 unpaired electron, and this unpaired electron gives it a paramagnetic character, okay. As you know here that carbon has the 4 bonds. Carbon usually forms the 4 bonds, and here also 1 unpaired electron is there. So the geometry will be tetrahedral, right? In CH3 positive, what is the case? That carbon hydrogen bond is there. It is sharing its electrons, fine, but the hydrogen which was earlier attached here, when it went, it also took. What happens here? Here, suppose any more electronegative atom was attached. Assume anything. Let's suppose it as A. So when it was broken, it also took away the electron of carbon. So what is the scene here? That 3 electrons are still with this carbon, but here there is a vacant orbital. There is no electron here. So here it is forming 3 sigma bonds of carbon and hydrogen, but here a vacant orbital is there, and this vacant orbital is diamagnetic. Okay, let's discuss the case of CH3 negative. Here what is the case? That carbon was forming 3 bonds, and here any atom was attached which was less electronegative than carbon. Okay, suppose it's B. So it was attached, and what happened? When there happened the bond breaking, what happened? Carbon took its electrons back along with the electrons of that leaving thing. So what is the case here? That carbon is still forming its 3 bonds, and in the orbital there are 2 electrons. Fine. So electron pair is there. Electron pair is there. and due to this pair it is again diamagnetic. As you know that in CH3 positive, what is the case that only 3 bonds are there, one is vacant. Fine. So what will be the geometry? The geometry will be trigonal planar. Fine. Now let's discuss about electron displacement effect. So why first of all electron displacement effect happens? It is natural. Whenever there is an electron, due to some electronegativity difference or due to some other things, what will happen? These electrons will be displaced up to a little extent from somewhere to somewhere. It usually happens. So electronic displacement effect can be of two types. Either the electron displacement is every time present there, so in that case it is permanent, or it comes due to any effect and then it goes, so that is temporary. So in permanent one there are three kinds of effect, that is inductive effect, then resonance one, then hyperconjugation. In temporary, there are two types, that is inductomeric second one is electromeric. So what are these electronic displacement effects? We will read one by one. Okay. So we have to find that CH3 positive, CH3 negative and CH3 free radical will be classified as Lewis acid or Lewis base. So if you remember from the ionic equilibrium that Lewis acids are the compounds that accept lone pair, right? Why? Because either they are deficient of electrons or you can say there is a vacant orbital, right? In the Lewis base, what happens that they can donate the lone pair. For example, in NH3, this is the lone pair, right? And this NH3 can donate this lone pair in any vacant orbital. That's the concept of Lewis base, right? So far CH3 positive is discussed. As you know that it contains a free vacant orbital, right? So means it is capable of accepting the lone pair. Therefore CH3 positive is the example of what? It is the example of Lewis acid. Okay. Then CH3 negative. As you know that this contains an extra electron in the vacant orbital, means it is similar to the lone pair, right? So what is this? It can donate its electrons, or you can say the lone pair. So it is the example of what? Lewis base. Okay. So far CH3 free radical is concerned, you know that there is neither the extra charge nor the deficient charge. What happens in this case? That the electron of carbon, that electron carbon has taken back. There is nothing extra, nothing deficient. So it is neither going to donate nor to accept. So it is nothing. So that was the concept of Lewis acid and Lewis base. Now if I ask you the geometry of all these, that is CH3 positive, CH3 negative and CH3 free radical. So CH3 positive, as you know, there are only 3 bonds, right? So what is this? This is sp2 and it is planar. In fact, I should say trigonal planar. In CH3 negative, as you know that there is the bonding electron present, right? So it is sp3 and it is tetrahedral. In CH3 free radical, what you know that the carbon's electron is with itself. There is nothing extra nor deficient, but it has the 3 bonds. So the 3 bonds means sp2 and sp2 is trigonal planar. So that's the concept of hybridization and geometry in these intermediates. As we have already discussed, dia is CH3 positive, CH3 negative is also dia, and CH3 free radical is paramagnetic. Okay, so it has been already done. If I draw the diagrams of CH3 positive, CH3 negative and CH3 free radical, so it will look like this. It is the diagram of CH3 positive. You can observe that here it is vacant, here it is vacant, right? I should remove the electron, otherwise you will get confused that there is an electron, right? So it was the diagram of CH3 positive, and how we identified? We identified by watching these vacant orbital. If we discuss the case of CH3 negative, so it will have 3 bonds and the lone pair will be here. Why? Because valence shell electron pair repulsion theory, it will occupy the state, or you can say the location where it gets minimum repulsion. So it is CH3 negative. And how we identified it? We identified by this free lone pair or
classes, these gaps go unnoticed. With one-to-one mentoring, chemistry becomes logical and real improvement begins.